The story of physics begins with humanity's natural curiosity about the world and its workings. As early humans observed natural phenomena like the motion of the stars, the changing seasons, and the behavior of objects, they began to seek explanations. Over millennia, this quest for understanding developed into the formal study of physics, a discipline that seeks to explain the fundamental principles governing the universe. Ancient beginnings, early ideas about the universe. 1. Ancient civilizations, including the Babylonians, Egyptians, and Greeks, laid the groundwork for early physics. 1. They observed celestial bodies, created rudimentary calendars, and studied the properties of objects like levers and pulleys. 2. In ancient Greece, thinkers such as Thales of Miletus and Pythagoras proposed early ideas about the nature of matter and the universe. 2. Thales believed everything was made of water, and Pythagoras linked mathematics to the physical world. 3. Democritus, a Greek philosopher, introduced the concept of the atom around 400 BCE, suggesting that all matter was made up of tiny, indivisible particles. 4. Aristotle, 384–322 BCE, one of the most influential early thinkers, developed a comprehensive system of physics. 4. He believed that everything in the universe was made of 4 elements: earth, water, air, and fire, and that objects moved according to their nature. 4. His ideas, while later proven incorrect, dominated Western thought for centuries. The Classical Era, the foundations of modern physics. 1. In the Islamic Golden Age, 8th to 13th centuries, scholars in the Middle East, like Ibn al-Hazan, made significant contributions to optics and mechanics. 1. His work on light and vision laid the foundations for the field of optics. 2. The Renaissance in Europe, 14th to 17th centuries, marked a revival of scientific inquiry, leading to the scientific revolution. 2. One of the key figures in this period was Nicolaus Copernicus, who, in 1543, proposed the heliocentric model of the solar system, where the Earth and planets revolve around the Sun, challenging the long-held geocentric view of Aristotle and Ptolemy. 3. Galileo Galilei, 1564–1642, often called the father of modern physics, made groundbreaking contributions to mechanics and astronomy. 3. He developed early telescopes and provided strong evidence for the heliocentric theory. 3. Galileo also discovered the laws of motion, showing that objects fall at the same rate regardless of their mass. 4. Johannes Kepler, 1571–1630, formulated the laws of planetary motion, describing how planets move in elliptical orbits around the Sun. 5. The most influential figure in classical physics, Isaac Newton, 1642–1727, unified much of the knowledge of his time with his book, The Principia Mathematica, 1687. 5. Newton developed the laws of motion and universal gravitation, which described how objects move and interact in the physical world. 5. These laws became the foundation of classical mechanics and were used to explain the motion of everything from falling apples to planets in orbit. The Age of Enlightenment and the rise of classical physics. 1. During the Enlightenment, 18th century, physics continued to develop, with major advances in the study of electricity and magnetism. 1. Benjamin Franklin and others began to understand the nature of electrical charge. 2. In the 19th century, James Clerk Maxwell unified the fields of electricity and magnetism into a single theory, called electromagnetism, with his famous Maxwell's equations. 3. Michael Faraday discovered that changing magnetic fields can induce electrical currents, leading to the development of electromagnetic induction, which is fundamental to modern electrical technology. 4. The study of thermodynamics emerged in the 19th century, driven by the need to understand the efficiency of steam engines. 4. Key figures like Sadi Carnot, Rudolf Clausius, and James Joule developed the laws of thermodynamics, which describe how energy is transferred and conserved in physical systems. The revolution of modern physics. 1. By the early 20th century, classical physics could not explain certain phenomena, such as the behavior of light and the structure of atoms. 1. This led to the birth of modern physics. 2. Albert Einstein revolutionized the field with his theory of relativity in 1905. 2. His special theory of relativity introduced the concept that space and time are interconnected, and that the speed of light is constant for all observers. 2. Einstein's famous equation, E equals mc squared, showed the equivalence of mass and energy. 3. Einstein's general theory of relativity, 1915, extended these ideas to gravity, describing it not as a force but as the curvature of space-time caused by massive objects. 3. This theory provided new insights into the workings of the universe, including the prediction of black holes and the bending of light around massive objects. 4. At the same time, quantum mechanics emerged to explain the behavior of particles at the atomic and subatomic levels. 4. Max Planck introduced the idea of quanta in 1900, suggesting that energy is emitted in discrete packets. 5. Niels Bohr developed a model of the atom in which electrons move in discrete orbits around the nucleus, with energy levels quantized. 6. Erwin Schrödinger and Werner Heisenberg formulated the wave mechanics and matrix mechanics interpretations of quantum theory, respectively. 6. Heisenberg's uncertainty principle stated that it is impossible to know both the position and momentum of a particle with absolute precision. 7. Quantum mechanics and relativity are the cornerstones of modern physics, and while they describe different realms, quantum mechanics for the very small and relativity for the very large, both are essential for understanding the universe. The 20th century and beyond, the search for a unified theory. 1. Nuclear physics emerged as a major field in the early 20th century, with the discovery of the nucleus by Ernest Rutherford and the development of quantum field theory. 2. The discovery of the neutron by James Chadwick in 1932 furthered our understanding of the atom, leading to the development of nuclear energy and atomic weapons. 3. The Manhattan Project during World War II led to the development of the first nuclear bombs, demonstrating the immense energy locked within atoms. 4. Post-war, physicists sought to unify the forces of nature under a single framework. 4. The Standard Model of Particle Physics, developed in the 1970s, describes three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. 5. The search for a grand unified theory, GUT, which would unify all the forces of nature, including gravity, remains one of the biggest challenges in physics today. Conclusion: physics today. Physics continues to evolve, with ongoing research into areas like dark matter, dark energy, and the origins of the universe. The discovery of the Higgs boson in 2012 confirmed the existence of a particle predicted by the Standard Model, adding to our understanding of fundamental particles. The development of quantum computing and advancements in cosmology are shaping the future of the field. Physics began with a desire to understand the natural world and has since transformed into a highly sophisticated and mathematical discipline, capable of describing the universe from the smallest particles to the largest galaxies. The quest for a deeper understanding of reality continues to drive scientific inquiry today.